images, um, and they're still pretty great. And these are sort of objects that exist at lots of different scales. So gas clouds sort of exist at lots of different scales. Here's about 10 light years, 100 light years, 1,000 light years, and 10,000 light years, approximately. And these are all different types of objects. So these are big gas clouds created, these two right here, when stars sort of die and explode. This is the Crab Nebula, which is a star that exploded sort of since humanity has been around. I think it was about 1,000 years ago. This one right here is a much bigger cloud, 10 times bigger than this one. It's called a molecular cloud. It's lots of gas that is sort of collapsed under gravity. And this is what we call a stellar nursery, because that collapsing gas can begin to form stars. So this is where sort of stars are formed. And then there's even gas clouds that sort of extend, that are outside of our galaxy and falling into the galaxy. These are what we call high velocity clouds. And these high velocity clouds are intergalactic gas clouds, so massive gas clouds that are falling into the Milky Way. So that was enough talk about gas. Let's talk about other galaxies, stuff outside of the Milky Way. Is there a question?
Waiting to change it.
Oh, okay. You were right. It didn't change. Okay, this is where the talk begins to get a little more interesting. This is where we start to talk about stuff outside of the Milky Way. So what we're looking at right now is the local group. And the local group is the collection of galaxies that are sort of our immediate neighbors. And here's the Milky Way in the center here. There's a lot of stuff around the Milky Way. And then what you might be familiar with is the Andromeda galaxy right here. And the Andromeda galaxy is our sort of largest and nearest cosmic neighbor. It's about 2.5 million light years away. And so just to emphasize again, because this blows my mind all the time, how far away that is, it would take light, the fastest thing in the universe, 2.5 million years to get there. What was Earth like 2.5 million years ago? Homo sapiens weren't even on the scene yet. Our sort of like ancestors were Homo habilis, began using stone tools around this time. So 2.5 million years ago was the beginning of the Stone Age on planet Earth. So if there was an alien with sort of a massively amazing telescope right now in Andromeda, they wouldn't be seeing us. They would be seeing Homo habilis developing the first stone tools, which is pretty crazy. Yeah, so, but we can go bigger. That's like the whole point of this talk. We can go even bigger. All right. So we throw the local group up on our cosmic ruler. You might notice we're getting awfully close to the end. I go again. Okay. So now we get all the way out to what like sort of our local galactic neighborhood looks like. The local group is sort of our immediate neighbors, but this is sort of more of like the city or the state that we're in. Yeah, let's call it the state of galaxies. So the local group is here. It's not really a big cohesive thing because the local group is not that many galaxies, so it's kind of hard to see, but it's like roughly here. And then there's sort of all these sort of groups of galaxies that we call galaxy clusters going along in this line. And then you might notice there's a really, really big one over here. This is what we call the Virgo cluster. There are thousands, I think approximately 2,000 to 3,000 galaxies in that cluster alone. And so this is about an order of magnitude larger than the local group. Actually, this is like 2 orders of magnitude larger. I should be specific, given that I have a ruler that's going to fact check me in a second. And the fun thing about this image is that you might notice there's also these things, instead of just clusters, which is the stuff we like to pay attention to, there's also these things called voids up here. So there's also regions in the universe that sort of have like an underdensity of galaxies. And so, and it's sort of not obvious that galaxies would be distributed in this way, meaning that instead of being sort of randomly distributed throughout the universe, there are sort of clusters, and there are sort of these like lines. You might notice it's a line here. I'm going to really emphasize the line in a second. There are sort of regions that have lots of galaxies and those that don't. And so this is not sort of intuitive, and it's sort of hinting at a sort of a much larger structure that sort of underlays the universe. So we go, and you can go one more. Actually, you can go one more again. Okay, there we go. And so what I want to emphasize here is that the galaxies that are sort of nearby us all sort of fall on this line. Why do they fall on a line? What's the deal with that? And it's because galaxies are not randomly distributed throughout the universe. They fall on this thing that we're going to call the cosmic web. And this is one sort of arm of that cosmic web. More technical difficulties. And so what happens if we zoom out one more time? Perfect. We begin to see what is actually a much larger sort of web-like pattern to the way galaxies are distributed in the universe. So that little line that I was showing you before is this line right here, which is showing up really nice, actually, which is kind of nice. So here's the Milky Way. Here's that big cluster of galaxies I was showing you. And here's that sort of line I drew. But that picture of the sort of nearby galaxies, if nearby is even a word you could use to describe that, is just one sort of filament on a much more larger web-like structure that is all sort of connected here. And this is what we call the Laniakea supercluster. And these are not sort of galaxies that we're sort of gravitationally bound to or anything. These are just galaxies that we're all sort of flowing towards the same place. These lines sort of represent where galaxies are moving in our sort of chunk of the universe that we occupy. So anything that's sort of in this orange bubble here is all stuff that's sort of generally moving in the same direction as us. And all the stuff out here is all sort of moving into these different sort of chunks of superclusters outside. And so this Laniakea supercluster is sort of the biggest coherent thing that we can say that we are truly a part of in the universe. As we zoom further out, which we will in a second, we're going to see that the universe is actually just filled with lots of things like this. So the Shapley supercluster over here, the Coma supercluster, the Perseus, there's actually a second word to that over there, I don't remember, and the Laniakea supercluster are sort of cookie cuttered throughout the universe. So let's zoom out one more time. There's Laniakea. We're getting really close to the top. There we go. So if we take Laniakea and we begin to zoom out even further, you can see that this web-like pattern begins to appear. So all those filaments I was showing you are actually the filaments that you're seeing on this sort of web-like diagram here. And if we zoom out even further, we see that this is just, you just begin to see more web. So this is what we call the cosmic web. As you zoom out further and further from here, you're just going to see more and more web. And Laniakea supercluster here, this is like a big galaxy cluster like the Virgo supercluster I was showing you. And then that filament I was showing you before are sort of these little tendrily things coming out of those superclusters. And this is how galaxies are distributed in the universe. There's also these sort of darker regions where there's less filaments, and those are sort of voids, regions that don't have very many galaxies. And there are some regions that are sort of millions of light years, millions and millions of light years across that don't have sort of galaxies in them, or don't have very many. There's probably one or two. It's a big universe. And so this is what we call the large-scale structure of the universe, because the entire universe is filled with this kind of structure. And you might be asking, what am I actually looking at here? You're looking at a simulation. This is not sort of a picture that's very easy to take. We do have sort of data that backs up what the simulations show, so I'm not just showing you something that's imaginary or theoretical. This is something that's very well sort of confirmed and understood in sort of modern astrophysics. But we really understand a lot of it due to the work of simulation groups. I'm sure Tom will tell you a lot about simulations. Maybe not cosmic web, but maybe galaxies and stuff. We can zoom out one more time. Actually, no, you can just, flip this slide. You might be wondering, how wide is this image I'm showing you? And it's approximately 10 billion light years wide. Okay, so Laniakea is about 500 million light years wide. And if we keep zooming out like this, we get to this image here, which is about 10 billion light years wide. And this is actually about 1/10 of the observable universe in width. And if we zoom out, because we've been going by orders of magnitude, if we zoom out one more time, we actually get to the entire observable universe. So 10 times bigger than that web there is just this smattering of galaxies. You're not going to be able to make up much of the structure. It's just kind of this webby mess. But we've done it. We've reached the entire observable universe. So the universe is sort of filled with that cosmic web. The cosmic web is sort of made up of well, it's made up of a lot of things, but it's populated by all the galaxies in the universe. And all the galaxies in the universe have pretty much all of the stars in the universe, and all the stars in the universe sort of contain a lot of the planets in the universe. And the planet that we live on is somewhere in that mess. You know, in theory, actually, it's actually at the center. It's at the exact center, which you can ask me why. But yeah, so we started with you all the way to the left here, a human, and we went up 28 orders of magnitude, so 28 factors of 10, all the way up to the observable universe, which is 93 billion light years wide in proper distance units. So yeah, we can go one more slide. This is my sort of summary conclusion slide. Every sort of panel here, once again, I made it in red, so it's kind of hard to see. But every panel that you're seeing here is one order of magnitude jump in size. And so we started with humans, and we went to buildings and football fields and bridges and cities and states. Well, here's a country. This is supposed to be the US, but the moon is actually about the same width. So there's the moon. I would be remiss if I didn't include our friend the moon. Then there's planet Earth and Jupiter and the sun and a bigger star that we don't have in our solar system. Then we have the whole scales that exist on the solar system in this image. Then we have gas clouds. Then we have our galaxy. Then we have the galaxies that are immediately near us. Then we have the sort of clusters and superclusters of galaxies that we can call home, our sort of cosmic filament as well, our little chunk of the cosmic web. And our little filament is just one part of a much bigger Laniakea supercluster, which is just what the cosmic web is sort of full of, is Laniakeas all over the universe until we get to the observable universe. So, yeah, that is the talk. Yes, you can. There's another slide. We covered the entire universe, so there was a lot of content. So there's probably questions. Feel free to ask. Yeah.
How far away is the cosmic microwave background?
Yes, the cosmic microwave background is actually, by definition, sort of the edge of the observable universe, because it's the first light. Because okay, so when the universe had just sort of exploded from the Big Bang, not just exploded, but like 300,000 years after the universe exploded, the universe was just full of plasma. It was full of plasma and light. And so the light was just bouncing off all of the different sort of plasma molecules. And we can't see any further into that. Plasma is sort of opaque to light, meaning it's like looking at a brick wall. You can't see any further than that. But eventually the universe expanded, and that plasma and during recombination, the universe, all that light that was bouncing between the plasma, all of a sudden began to stream freely through the universe. And that moment is what we see in the CMB. And so that is the sort of earliest light that we can see. It's the furthest into the universe that we can see. And so by definition, the cosmic microwave background, that light that you're asking about, is at the edge of the observable universe. Yeah. Yeah, one question there. Yeah.
What's the theory of the cosmic split? Two questions.
Yeah.
What's the theory of the cosmic split? And then when you zoom out to the dark areas, is that like the dark energy that's involved? Also so that the fabric would thin out over time?
Yeah, so that's sort of a lot to say and answer that question. Oh yes, let me repeat the question. The question was sort of, when we're looking at these images of, let's say, Laniakea, what is causing the sort of different filaments to sort of be in different locations, and why is there a split there, and these regions that are sort of underdense, why are they underdense? And it's sort of a hard question to answer because the cosmic web it sort of forms out of just what happens if you put a bunch of matter in a box and you let it collapse under gravity. And unlike with, say, like, if you sort of explode a planet and then you let it collapse under gravity, it all sort of accumulates into one spot. But in the entire universe, the universe is filled with all this stuff. And so as it collapses under gravity, and dark matter is there collapsing everything under gravity, and you're right that dark energy is trying to pull everything apart. Yeah, I guess there's really no easy way to say why does it look like that. It's just kind of, maybe Tom has a better answer, but it's just kind of what happens when you put a bunch of stuff in a box and you let it collapse under gravity. Okay, yeah, right there.
The farther we look out, the farther back in time,
Yes.
is there evidence that the web looked different farther ago? How dynamic is the cosmic web?
Yes, that is a great question. So the question was, because the speed of light is finite, so what actually happens when we look out into the universe is that we're actually looking back in time the further out we look. And so the question was, if we're looking back in time into the cosmic web, does it look different? And the answer is it looks very different. This is the universe asterisk. The asterisk is, this is what the universe looks like today. When we actually sort of look at the universe and we're looking back in time, we look at this sort of cosmic web as it was when it was younger. And so there had been sort of less time for it to collapse. And so the web does look different back in time. There's no sort of easy way to describe how it looks different, but it hadn't collapsed as much as it has now. Yeah.
Last question.
Oh, last question. Okay, right there. Oh, what a great question. What is outside the observable universe? So, by definition, I can't give you an answer that's sort of backed up by any sort of observation, because we literally can't see any further. But I think that a general consensus would say that when you go outside the observable universe, there's a lot more universe that looks basically the same. It just keeps going. In the same way that as we zoomed out from the cosmic web, we just got more cosmic web. If you zoom out from the observable universe, it keeps going. The question is then, is the universe infinite? Is it finite? Who knows? Maybe it goes on forever, maybe it doesn't. The universe is pretty homogeneous, meaning it kind of looks the same everywhere we look within our observable universe. So, there's some reason to believe that as you look a little farther out that it would look the same as well, but there's no way, at least that I know of, to confirm how big the universe is as a whole. Yeah.
Let's thank Charlie one more time.
And you can feel free to ask me more questions after if you raise your hand.
Okay. All right. Good God, Charlie, you're tall. Good. All right. So before we go to intermission and then move to our second talk of the evening, it is now time to announce the trivia answers. And tonight we have 3 second-place winners that got 9 questions right, and we have 1 first-place winner who got 10 questions right. Was actually split into 2 teams, but we'll talk about them at the end and why they're in trouble. First, let me give you the trivia answers. Okay, number 1, this is Tom Quinn, Professor Tom Quinn, also known as Pirate Greybeard, and our second speaker of the evening. 540 million knots is the speed of light in pirate units. A factor of 10 is an order of magnitude. Saturn is approximately 1.5 light hours away from us. Alpha Centauri is approximately 4.3 light years away from us. Our ship, Earth, is sailing in the Orion Arm, that's true. 1 billion years would be how much time it would take the immortal Pirate Greybeard / Professor Tom Quinn, boarded on the Voyager 1, to cross the entire galaxy. The Laniakea supercluster is what we're in with 100,000 other galaxies. We're also in the Virgo supercluster, so you said that, you got that right too, okay. And none of these things are beyond the observable universe. And it's false that the immortal pirate graveyard, aka Professor Tom Quinn, has been to the edge of the universe unless he's lying to us. And so with that, let's announce the second place trivia winners. Thank you. Drum roll. Aliens. Yeah. You guys are great. Okay. Woe be gone. You guys ready? Nice. Okay, wait until the end to get the trivia. Sorry, should have said that. Wait until the end of the second talk to get your trivia prizes. You have to stay. Okay. And the last second place winner is Snoopy. Nice. Yeah. Okay. Now, as I go to announce the first place trivia winners, I feel like, I don't know if you guys know this, but I feel like I have to tell you that my research specialty, like my area of specialty, the thing that I love the most in this world, is exoplanets. You know who you are. You know what I'm about to say. Yeah. Okay, so the first place trivia winners, they got 10, right? But I'm actually going to knock them down to 9 because their team names were exoplanets are stupid. And exoplanets are still stupid. And you know what? You could have gotten 2 prizes, but your bad team name told me that you were in cahoots, so you get 1 prize. Okay? That's shame. Exoplanets are great. You might have thought that our next speaker, Professor Tom Quinn, aka the Immortal Pirate Graveyard, is a galaxy person, but he secretly loves exoplanets. He's exoplanets' #1 fan. So, take that. Okay, so with that, we're going to go for a 10-minute intermission, and then we will come back with Pirate Graveyard, aka Professor Tom Quinn, to give the second talk of the evening. Thank you.
Got it. Okay, switching. Let's switch. Okay. So you will take this. Sorry, this. It says the battery is fine. I don't know what's happening. And then it jumped out of the thing.